Right. So this is where I wanted to start today, is talking about activating groups. So activating groups. Now, we spent a lot of time last class talking about different reactions. We talked about nitration, sulfonation, and halogenation, being bromination and chlorination. We also talked about Friedel-Crafts reaction. So we talked about Friedel-Crafts alkylation, then we talked about Friedel-Crafts acylation, and we learned the Clemmensen reduction for reducing a carbonyl. And today we're going to mostly focus on the direction or directing groups. So we're going to talk about what are called activating groups, deactivating groups. And then if there's time at the end of the lecture today, I want to spend some time talking about synthesis strategies, because there's quite a few nuances in syntheses in chapter 18. But let's get started here in talking about activating groups. And it says that two issues arise when adding a group to a ring which already has one or more substituents. So consider the nitration of toluenes. Toluene, not an uncommon organic molecule. What if you wanted to nitrate that? Of course, you would treat it with nitric acid and nitric acid that produces the nitronium ion, and we went over that last class. But what kind of effect is the methyl group going to have on the rate of nitration? And it tells us here, it says that toluene actually reacts faster than benzene, and that is due to the fact that the methyl group is electron donating via hyperconjugation, which makes the ring a better nucleophile. And so the nucleophilic attack is going to occur even faster, okay? Toluene will be a better nucleophile than benzene will be. All right, so we know that it's going to react faster, and that's on account of the fact that the methyl group is electron donating. But what about the regio selectivity of the reaction, right? Where's the nitro group going to go? Is it going to go in the ortho position? Will it go in the meta position, or will it go in the para position? And of course, we have two ortho positions, we have two meta positions, and we have only one para position. So where is it going to go? And we're going to answer that question today. And what you see is that when you nitrate toluene, or you treat it with nitration conditions, it says here that the ortho and para products predominate, and you can see that reflected in the percent yield. We get 63% ortho, so that's the majority. Then we get 34% para product, and we only get a little bit, only 3% of the meta product. Okay, so we get very little meta product. And there's a good reason for that, right? There's a very good reason for that, and that is based on this sigma complex. So we need to take a look at the sigma complex in order for us to fully understand what's going on here. And so what's being shown is it shows the nitration occurring at the ortho position, the meta position, and the para position. And then the sigma complexes are drawn for each three of these, for the nitro grouping put at each three of these positions. And you'll notice that in the ortho and para position, when we have the nitration, at the ortho or para position, we have the positive charge adjacent or next to the methyl group. And I told you that the methyl group was electron donating. So we're going to say that the methyl group is an EDG. It's an electron donating group, right? It's an electron donating group. And so what's that going to do? That's going to partially stabilize that positive charge, okay, by the electron donation from that methyl group. So that means that these two sigma complexes that are highlighted in green are going to be lower in energy, right? They're going to be more stable or lower in energy, and therefore the energy of activation for the formation of the ortho product and the para product is going to be lower than that of the meta product. And you can see that in the meta attack, we don't have any case where we have the positive charge adjacent to that methyl group. And that's why it's so crucial that you are able to draw the sigma complexes and able to draw all of the resonance contributors, right? You should be able to draw each one of these resonance contributors. Of course, you can memorize, you can just memorize, well, a methyl group is going to be ortho and para directing, and that's totally fine. But as is the case always in organic chemistry, the more that you understand it, the easier that it seems to be. Okay, here's a reaction coordinate diagram for the ortho, meta, and para attack on toluene. And again, what I said is true. You can see that the energy of activation, and if you're wondering what's energy of activation, well, hopefully you know that by now, but the energy of activation is this energy here, okay? And I won't label it on all three, but you can see that on the ortho and para attack, it's pretty close, right? It's pretty close. The reason why it's a little bit higher on the ortho attack is because of sterics, right? It's a little more sterically hindered because of that methyl group, but a methyl group is pretty small, and so the difference in the activation energy of the ortho and para isn't that big. And in fact, the reason that we get more ortho product, the reason it's formed in 63% yield is because simply because there's twice as many ortho positions as there are para positions, right? And then you see here with the meta attack, because we don't have that stabilized sigma complex, you can see that the energy of activation is much, much higher, right? Very high energy of activation here, much, much higher, okay? Anyhow, so that's the rationale, right? And you should be aware of that moving forward in this chapter. Okay, so it says here, more ortho is going to be formed because there are two ortho positions and only one para position. And of course, I mentioned that on the previous slide, right? We've got two ortho positions, but we've only got one para position. So it just boils down to statistics, really, probability. Again, a methyl group can provide some steric hindrance, but again, a methyl group is not very big, so it doesn't really, in fact, it's basically an exception. If you have any alkyl group that's bigger than a methyl, then you will see that para will predominate, and we'll look at that later. Okay. What about a methoxy group? You guys remember this molecule, this old chestnut? Okay. If I draw anisole, which is, methoxybenzene. So if I draw anisole, what's the effect of this oxygen going to be, right? Because it's like a toluene, but there's an oxygen stuck in there, right? So it's an ether. Okay. And it says that it activates the ring 400 times more than toluene. That's a big difference, right? 400 times more. If it was, twice as much or something, that wouldn't be that big a deal. But 400 times more is a big difference. And there's a good reason for that. And that's because instead of donating electron density via hyperconjugation, it donates it via resonance, okay? So again, this is an electron donating group, but you can draw these curved arrows where you draw this lone pair, creating this double bond here, and then we have a negative charge here, and we can show that negative charge being delocalized throughout the ring like that. And that's the answer. That's why anisole is going to be so much more reactive towards nitration or sulfonation or halogenation, whatever. It's just because the pi bonds in here are going to be much more nucleophilic, right? They're more readily available. In fact, the methoxy group activates the ring so strongly that a Lewis acid catalyst isn't necessary, and polysubstitution is difficult to avoid. You probably remember from Monday's class that when we talked about the halogenation of benzene, right? If we took benzene and we wanted to make bromobenzene, or chlorobenzene, right? We needed a Lewis acid catalyst. We needed to have not only bromine, but we needed to have iron to make, iron tribromide. So we'll put here Br2 and iron 3 bromide like that. Anyhow, so we would need those. But now you see that with anisole, you don't need that. All you need to do is just treat it with bromine. And the reason why is because the ring is so strongly activated. If you're wondering, do I need to know this kind of nuance, this kind of, almost exception? And the answer is yes. Yes, you need to be aware of that. Okay. Now, something that you notice here is that when you take anisole, so here's our anisole molecule, and you treat it with just excess bromine, you notice that you only get bromination at the ortho positions and at the para positions, right? We get nothing, we get nothing at the meta position. And that's a generality, okay? That's a trend that we see here. It says activators are generally ortho-para directors. Now, activators are usually electron donating groups. So we could put here in brackets, electron donating groups like that are generally speaking going to be ortho and para directors. Like the methyl group, the methoxy group is activating and an ortho para director. But here, if we take a look at the percentages, you can see that para is actually the major product, and it's simply due to sterics, okay? Nothing more than that. And as I told you, the methyl group on on toluene. It's not very big, but once you get that oxygen in there, you have free rotation around this carbon-oxygen bond, which causes some steric hindrance. And so in this case, you're going to end up with more para than you would ortho. And of course, you end up with very little, almost next to none, very, very little nitro, or very, very little meta substitution. You can see that our book is very thorough when it comes to sigma complexes. Dr. Klein likes to always show all the sigma complexes so that students will understand, why do we get ortho and para attack preferentially? And you can see that here very clearly, okay? If you look at this resonance contributor here, okay, we have a positive charge on the carbon next to an oxygen. And, if you go all the way back to chapter 2 in Organic Chemistry 1, you know that that's going to be stabilized, right? We can draw this resonance contributor here. If you wanted to go from here directly to here, right, you would just draw a curved arrow like that, okay? And so not only is the positive charge stabilized throughout the ring, but it's also resonance stabilized by the lone pair on that oxygen. So there we go. And you can see the same thing occurring in the para, okay? You can see the positive charge here. And if I wanted to go from here directly to here like that, I would just draw a curved arrow like that again. And again, I'm repeating myself. The way the book is written is that when we have meta attack, we don't see that contributor, right? We don't have that fourth resonance contributor that we do when ortho and para attack occurs. Okay, give me a thumbs up if you follow me thus far. All right, we're still just kind of scratching the surface here, but you're going to see the same rationale come up over and over today. Okay, so if you understand it now, or if you just follow the rationale, good, thank you. Okay, perfect, good. That's great. You're going to find that the same rationale is going to apply throughout the chapter. Okay, so we're going to see the same concept coming up over and over and over. If you're the kind of person that needs a reaction coordinate diagram, here you go. Here's one for you. This is, again, just showing the reaction coordinate diagram of the nitration of anisole. And if you look at the activation energy for ortho and para attack, you see that there's more of a marked difference in activation energy for ortho and para attack with anisole than there was for toluene. If you go all the way back in the slides where we looked at the reaction coordinate of the nitration of toluene, you'll notice that the activation energies of ortho and para were much closer. And I explained, why there was a slight difference. But here, the reason that the ortho has a significantly higher activation energy is based on exactly what you're thinking, right? It's based on sterics, okay, which you've already discussed. So the activation energy is quite a bit higher than that of para, and that's why the para product is going to predominate. But then if we look at the activation energy for the formation of the meta-substituted product, you can see it's off the charts, right? It's way higher than that of the ortho or the para, okay? Anyhow, a picture is worth 1,000 words, and that's one thing I love about organic chemistry. There's plenty of pictures, lots of things to look at. Okay. Think about it, in organic chemistry, it's very rare to have a slide where there's just text. Okay, there's usually some kind of picture to take a gander at. It's nice. Okay. Anyhow, let's switch gears. So that was section 18.7. That was, let me back up. That was activating groups. Okay, that was the whole subject of section 18.7. Now, if you're wondering, is there a summary of activating groups? Absolutely there is, and we're going to take a look at that. Okay, so we will look at a whole summary of different activating groups because obviously there's more than just anisole and toluene. Okay, that we're going to look at a comprehensive list, or pretty much a comprehensive list later on. But before we do that, before we summarize, activating and deactivating groups, let's look at section 18.8, which deals with deactivating groups. If you understood, that's the great thing about organic chemistry. If you understand some of it, you can figure out a lot of it, okay? And if you understood the rationale for activating, for why, toluene and anisole, why the methyl and the methoxy were activating groups, you'll be able to understand deactivating groups, okay? And if you're still kind of like on the fence, like, oh, I'm not sure if I understand, well, follow me carefully and you'll get it, okay? So it says here that a nitrate or nitro group is an example of a deactivating group. This is a nitro group, okay? So if I draw this, okay, so I'll draw, this is nitrobenzene, Okay, nitrobenzene. And this is the Lewis structure of the nitro group. Everybody who's hearing the sound of my voice should be able to draw the Lewis structure of a nitro group by now. It says here that it is both inductively electron withdrawing. Okay, so we can draw this dipole moment going this way. We've got a positive charge here. So, of course, that's sucking electron density away from the ring. Yeah, of course it is. But also we can draw these beautiful resonance structures here where we show the positive charge, delocalized throughout the ring. Now, let's think about it. The activating groups were donating electron density to the ring, right, which was making the pi bonds more nucleophilic, right? They were ready for a nucleophilic attack. If we have a positive charge, delocalized throughout that aromatic ring, what does that tell us in these resonance structures? It tells us that electron density is being withdrawn from the ring, right? It's pulling it away. And so we call this deactivating group, we call an electron withdrawing group, an EW, that wasn't supposed to happen, an EWG. Okay, so you need to know what an electron withdrawing group is, and you should be able to draw all of these resonance structures that are shown here. All right, and again, it's just got to do with the fact that we're pulling electron density away from that ring, and so it's, these pi bonds are not going to be very nucleophilic, right? They're not going to want to do a nucleophilic attack. Okay, in fact, I should have drawn it like that because meta will predominate. Anyhow, we're going to look at that more in a second here. Ta-da. Let's move on. Chemistry is content driven, right? Anyhow, what about the rate? If you're the kind of person who is thinking, when you mentioned toluene and then you mentioned anisole, you mentioned the rate of reaction. Well, what about the rate of reaction with nitration? And what you're going to see is that it's crazy how much more deactivated nitrobenzene is compared to benzene. It says here that nitrobenzene undergoes nitration 100,000 times slower. That's a lot slower. Okay, so that tells you that the nitro group has a profound effect. Okay, a very profound effect. And it's going to be much more difficult to substitute rings that have deactivating groups on them. In fact, if we want to do the nitration, we treat it with nitric acid and sulfuric acid. We have to crank up the heat, okay, to 100 degrees Celsius. So that's the first thing. It's a lot slower. Now, I'll be honest with you guys, in organic chemistry too, whether it's an ACS final or a DAT or an MCAT or a PCAT, whatever, standardized exam, or whatever, anything to do with organic chemistry that's got the standardized exam, they're not going to be as concerned with the reaction rate, I don't think, as where is substitution going to occur. And what you need to know is that when you have a deactivating group, generally speaking, you're going to get the meta product. Look at that. Meta product, 93%. In fact, very little ortho, very little para. Okay, that's a big difference. This is a pretty useful reaction when you think about it. Right, 93%. That's a pretty good yield. And if you had to purify this, and you only have to remove 7% overall of side products, I mean, as long as you can find good conditions to recrystallize the compound or maybe purify it by column chromatography or something, that's a nice reaction. In fact, don't think, oh, it's 100,000 times slower, it's useless. No, I'd say if it works in 93%, hey, I'm there. Anyhow, I've done lots of reactions that aren't 93% yield, I can tell you that. Anyhow, so deactivating groups, let's take a look at the sigma complexes, right? Our book, again, is very thorough at always showing these are just the sigma complexes for the ortho, meta, and para attack. And what you see is an effect that's going to, I guess it's like a destabilizing or a deactivating effect. I'm trying to search for the words for it here. But it's manifested in these two sigma complexes, these two resonance contributors that are shown here in green. Now, what's the problem here? Actually, I haven't asked my students a question yet. But could anybody tell me what's the issue here, with these two contributors that are highlighted in green? It doesn't have to be some fancy answer. It's just, you might. Anyhow, I'll let you try and answer before I interrupt. Does anybody have an answer? Electron withdrawing group is sad. Okay. Yeah, that's one way of putting it. Right. It's just, these two contributors these two resonance contributors are destabilized. Okay, so let's use that as our word. We'll say destabilized, right? Because you're not stabilizing this positive charge, you're destabilizing it because you're pulling electron density away from a positive charge. That's not going to help, right? The same thing is occurring here. You're pulling density away from a positive charge. That is going to destabilize that resonance contributor, okay? And so that is why the meta attack is going to predominate. It might be slow, but we don't see that destabilizing effect manifested in any of these resonance contributors. There's no positive charge here, here, or here. It stays away from the carbon adjacent to that nitro group. Give me a thumbs up if you follow me on that, on destabilization. Just the rationale for destabilization, or a deactivating group, I should say. Cha, I've only got one thumb here. Is it because it's Friday? Are there any questions about this? If you have a question, feel free to interrupt. Feel free. All right, one thumbs up. Thanks, David. All right, there we go. Okay, so if you're the kind of person that needs a reaction coordinate diagram, we have again potential energy on our y-axis. Reaction coordinate just means the progress of the reaction over time, but you see that the activation energy for ortho and para is just much higher than that of the meta. None of them are low, right? If you think back to all of the reaction coordinate diagrams that we've looked at today, the first two or three of them, or the first one, all the first ones that we looked at until now, they all involved activating groups, right? And now that we're into deactivating groups, did you notice that he tries to be consistent on the y-axis, and that the activation energy of meta, even though it's the preferred product, it's higher, you know, it's quite a bit higher than it was, like the ortho ones, and the other ones are quite a bit lower. Anyhow, I'm probably not helping. But anyhow, there we go. All right, so now we're going to switch gears, and, you know, as one of my students so aptly put it, you know, what is organic chemistry? It's learning a bunch of rules and then the exceptions to those rules. But I'll give you a good one here, is that we got a whole section of a chapter devoted to an exception. So it must be a pretty pronounced section, pretty pronounced exception if there's a whole section of the chapter devoted to just that. Okay, and it's the halogens. And we've already learned how to do halogenation. We learned how to do chlorination and bromination. So the halogens are, in fact, an exception. If you think about a halogen, you know, on an aromatic ring, let's just draw one out here. We'll put a chlorine. Let's put a chlorine, okay? Well, chlorine is a pretty electronegative element. What's the electronegativity of chlorine? It's around 3.5, 3.5, something like that. So, no, sorry, it's around 3. Jeepers, Mr. Deon. Gotta wake up. Okay. So the electronegativity of chlorine, you might be wondering, well, would chlorine be activating or deactivating? Well, you can see the answers on the slide. But why is it? Because chlorine, if it's got an electronegativity of 3.5, thereabouts, okay, so that means it's electron withdrawing, okay? But hold the telephone, right? It can also donate electron density, right? It could do that. No reason why not. So then you're wondering, oh, shoot, which one is it? What's going to be the governing factor here? Is it going to be, the electron donation based on resonance, or will it be the electron withdrawing effect based off of the electronegativity? Excuse me. Well, I'm glad you asked that question, because I have the answer right here on the next slide, okay? Halogens do withdraw electrons by induction, so they are deactivating, but they also donate electrons through resonance. So this is the exception, okay? Halogens are deactivating, but they're ortho-para directors. That's the answer to 18.9. That's the whole thing summarized in one sentence. A halogen is deactivating, but it's an ortho-para director because of resonance. Done. That's it. Okay? So let's take a lookie if we were to do a nitration on chlorobenzene, here are the sigma complexes for the ortho, meta, and para attack. Again, you know, that chlorine is pulling electron density away from the aromatic ring, which is going to slow down the reaction, right? It is deactivating it. However, when you look at where the substitution occurs, right, the Regio Selectivity, you see that for ortho and para attack, even though we have a deactivating group, we have that one extra tasty, beautiful resonance contributor, okay, where we can delocalize that positive charge up onto the halogen, which is an extra contributor. And so the activation energy for ortho or para attack is going to be lower than that for meta attack. Okay, so that's just an exception. Everybody has to know it. And if you're wondering, you know, do these exceptions like that anisole exception that you showed us with the halogenation, or this, you know, exception that's in 18.9, could these ever show up on the ACS model? Absolutely. Okay, absolutely, these are exceptions. Okay, that's why this is a 3-day chapter, because these are very important exceptions that everybody has to know. So let's take a deep breath here. Let's kind of summarize what we've learned in the past 3 sections, and that is shown right here. The directing effects of a substituent. A strong activator is going to be, so anything that's an activator is going to be ortho-para directing, right? So a strong activator, these are things that have a lone pair on a heteroatom on an aromatic ring. So whether it's an oxygen, so we have like a phenol derivative or a phenoxide, or an aniline derivative, or some kind of substituted, you know, alkyl group put on an aniline like that, right? And you should be able to demonstrate why these are ortho-para directors, right? Because you could always draw these resonance contributors that show a negative charge being delocalized throughout a ring. A moderate deactivator is going to have a heteroatom with a lone pair, just like the strong activators, but it's going to usually have an electron withdrawing group, you know, next to it like this, you know, that can pull electron density away like this. So you got, you know, you got something that can donate electrons into the ring, but you got something else vying for its attention, right? You get something else that can pull electron density away from it. I'll be honest with you guys, I've taught this class long enough to know that most students just memorize these, and that's totally fine. There's one here that's kind of an outlier in my opinion, and that's this one here, is the phenylether. You know, you might be thinking, well, why this be down in moderate? Because I don't have a carbonyl here, right? Shouldn't it be up here with the strong activators? Well, why don't we say that a phenylether, I have written in my notes, it's kind of in between moderate and strong. So we'll put here in between moderate and strong. Now, weak activators, those are alkyl groups, okay, like methyl, ethyl, isopropyl, tert-butyl. All of these are going to be weak activators. Still ortho-para directing, right? Electron donating via hyperconjugation, but they're only going to weakly activate the ring. All right, well, let's take a look at deactivators. Strong deactivators, of course, you recognize nitro. We talked about that enough. If you have a nitrogen with a positive charge, so this would be like an anilinium derivative, you can't draw a resonance contributor where you draw, now don't do this, okay? You can't put a bond like that, because then you'd have 5 bonds to nitrogen. Nitrogen is in the second period, it can't exceed an octet. You can't do that, but you do have a positive charge here, and so you can see that it is pulling electron density away from the ring. I can't even remember that example coming up in our textbook, so let's see. Or if you have a toluene derivative that has, you know, that is completely halogenated. So if you have trichloromethylbenzene or tribromomethylbenzene or trifluoromethylbenzene, right, something like that, that would be deactivating, a strong deactivator. Why? Because you'd have what? You got 1, 2, three dipoles pulling electron density away from the ring like that. So strong deactivators. Moderate deactivators are something usually that has a carbonyl, okay, a carbonyl directly attached to the ring, right? And you could draw the curved arrows for any of these. I won't do it for all of them. And then the last one, this is a sulfonic acid, and this one here, this is called benzonitrile. So this is a nitrile derivative, and again, you could draw the same resonance contributors that show a positive charge being delocalized throughout the ring, which again demonstrates why the ring is electron deficient. It's going to render it less nucleophilic. Okay, and weak deactivators. Remember, this is the big exception. Here's the halogens. Look, 18.9. One exception to remember, that's the halogens, okay? Weak deactivators, okay, on account of what? Induction, or their electron withdrawing capabilities, because the halogens are electronegative, okay. But they're going to be ortho para directing because of resonance, because they do have that one extra resonance contributor in the sigma complex that we looked at a few minutes ago, okay? Activators and deactivators are summarized in table 18.1. I don't think it would be a bad idea to memorize this table, okay? Instead of putting the word memorize, I'll just put know this table, okay? Make sure you know this table, know everything on it. It's a nice summary. We have ortho para directors at the top. Those are all activators except for the halogens, which are weak deactivators, but again, ortho. And the meta para directors, those are all summarized here as well, okay? So something that's deactivating. All right, that's a lot of information, you know, that we've just covered. So I think what the best thing to do now would be to tackle some problems, right? Take a look and just start with the basics, okay? Start with the basics and see if we can recognize activators and deactivators and decide where substitution is going to occur. So make a decision on reactivity and or activator or deactivator, and then make a decision about regio selectivity. And we'll do that with this question right here. Question 18.16. I'll give you a second to take a look at it. It's freezing cold down here in my basement, so I'm going to put a jacket on. Okay, so I'm going to be calling on my students here for some sweet, sweet answers. Let's start with 18.16. A, it says for each of the following compounds, predict whether the ring is activated or deactivated, then predict the strength of activation or deactivation, and finally, predict the expected directing effects. Who could help me out with A? We'll start with activation or deactivation. Would this be an activator, deactivator, strong activator, moderate deactivator? Who's got an idea? A nitro group, nitrobenzene. Yeah, it's a strong deactivator, right? It's definitely a deactivator, that's for sure. And it was one of the strong ones. So let's write that down. We'll put strong deactivator. And where is that going to direct? Ortho, para, or meta? Yeah, it's going to direct at the meta position. Okay, let's move on from there. We have an acyl group, so we have a carbonyl here. We could draw a resonance contributor like that. So would this be activator, deactivator? Who could help me out with this one? Moderate deactivator, absolutely. Thanks, Adriana. So this would be a moderate deactivator, okay? And if we have a moderate deactivator, just like a strong deactivator, it's going to be meta-directing. The next one is a halogen, right? A halogen, we already know that the halogen are ortho and para directors. We covered that in detail, but they are weak deactivators, okay? They are only weakly deactivated. So we'll put here weak deactivator, like that, okay? And this last one is kind of an interesting one. We didn't see this, you know, exact group here showing up on our table 18.1, but you could draw a resonance structure where you could delocalize, you know, so we'll put the lone pair in here. We could move these electrons around like this and like this. And I'll kind of help you out with this one. And then we'll take a good hard look at it. So we'll get a resonance contributor that looks like this, where we have the negative charge on our nitrogen like this, and we'd have a positive charge like that. And so you can see that this is pulling electron density away from the ring by resonance, just like in B. And so it's got the same kind of effect that a carbonyl has. And thus the conclusion would be that this would be a moderate deactivator. Deactivator, like that. And we know that deactivators are going to be meta-directing, unless it's a halogen. Okay, there we go. Well, let's move on from there. So that's just kind of, being familiar with what? I'd say table 18.1 is kind of the whole crux of this question, is making sure that you know that table inside and out. Well, let's talk about, I bet you somebody who's been listening today, or probably all of you, have been thinking, well, hold on. It's all well and good if I have one group on the ring. What's going to happen if I have a bunch of different groups on the ring? Then what do I do? Where does substitution going to occur? The answer is sometimes it's easy to figure that out. Sometimes it's not. And it's very rare for me to use the word easy in organic chemistry class, but I'd say maybe not easy. I'll put it this way. Sometimes it's abundantly clear, and then sometimes you have to think about it a little bit harder. Let me show you some examples, and you'll get it. Okay, so multiple substituents. The directing effects of all substituents attached to a ring have to be considered when we're studying an electrophilic aromatic substitution reaction. The directing effects of a methyl group and a nitro group direct the bromine to the same carbon, so we only get one product. This is one of those examples that I'd say it's abundantly clear. A methyl group is an ortho para director. That's going to direct to these positions. You can see that the para position is blocked, so it can't go there. And then a nitro group is a meta director. Here are the meta positions, so you've really only got one position that the bromine can go to. So I'd say this one is, I shouldn't say things like no-brainer in class, but I'd say this one is, again, abundantly clear. Give me a thumbs up if you follow me on that. You're like, I think I could make that kind of decision. Yes? Does everybody follow me on that? You got two groups. They direct to the exact same carbon. Boom. No side products to really concern yourself about. Just write down the product and move on with life. Okay. Well, let's look at something, let's get a little bit more down and dirty with it here. What if we have, it says here, if the groups direct to different carbons, the stronger group is going to dominate. So let's take a look here. We got a hydroxyl. We got a hydroxyl here. So we know that a phenol, we looked at this in table 18.1, is a strong activator. And then we have a methyl group, which is an activator. Yes, absolutely, it's an activator, but it's weak. And so the hydroxy, or the phenol, is going to direct to the ortho positions. The para position's blocked, so it can't go there. Now you might be thinking, no, what about the methyl group? Wouldn't it direct to the ortho positions? Now the para is blocked too. But the answer is we're going to go with the strongest one, right? We're going to go with the stronger activator. And so the nitration from nitric acid and sulfuric acid would occur ortho to the hydroxyl. Okay, so it's going to occur at this position. Does everybody follow me on that one? It's kind of hard to interact with my students over Teams, but give me a thumbs up if you follow me. If you don't, feel free to ask me a question. We can stop. We can park. Okay, good. All right. Well, let's go on from there. Steric hindrance has to be considered when more than one product is possible, and we're going to use these guidelines. Okay, so here's where it gets a little bit more entertaining. Okay, so we're going to address your question, Mauricio. If they're of equal strength, I'll address it partially right now, Mauricio. There's always going to be some deciding factor that you can make. And if you're wondering, well, if I have two methyl groups, well, where is it going to go then? Well, it's going to have to only go to one position, because we don't focus on poly substitution really in this class, except for that one specific case with anisole. Anyhow, Let's take a look here. It says, point number 1, for a monosubstituted ring, the para product typically dominates due to sterics. Here we've got that we've got the isopropyl group. So this isopropyl benzene, well, that would be acceptable. It's called cumene. If we nitrate cumene, it's going to go, the nitro will mostly be in the para position. Okay, again, this is an ortho para director. So nitration is mostly going to occur in the ortho and para positions, but it's going to go mostly in the para position due to sterics. Okay, and I will even do you one better here, and let's write it in here. We'll put toluene. Let me choose a different color. Toluene is an exception to this. Toluene is an exception. And that even depends on the conditions. Because if you think about it, at the very beginning of this lecture, we looked at the nitration of toluene, and we saw that the ortho substituted product was the major product, and that was just based on the methyl group being so small, but an isopropyl group is much bigger, and so the para substitution is going to predominate. Okay, let's move on from there. Number 2, for 1,4 disubstituted rings, substitution is going to occur at the less sterically hindered site. So if we look at the isopropyl group, we've got an ortho para director here, we've got an ortho para director here. They're both weak activators, so they're going to be in competition with each other. But based on steric hindrance, right, the nitro group is going to mostly go in this position, which is ortho to this methyl group, which is smaller. Right, you can get some of this product, which is ortho to the isopropyl group, but remember, they're both weak activators. It's not like one of them is weaker than the other. They're anyhow. That's not the issue. The issue in this case is going to be governed by sterics. Okay, so that we make that decision. If you've got a 1,3 disubstituted ring, it's not very common for substitution to occur in between two alkyl groups. Very rarely do we get that. And so here we have, again, our 2 weak activators. They're both ortho para directors, right? Ortho para directors. And so it might be a knee-jerk reaction to say, hey, it's going to go right here because that's ortho to both of them. That should be the major product. But in fact, we don't get any of that, and that is just solely based on sterics, right? It's just too sterically hindered to get into that spot. And so we're going to get this as our major product, okay? Why would that be major? Because it's ortho to the smaller group, right? This is ortho to this position. This is ortho to this position, which is a bigger substituent on it. Nothing more than that, okay? That's the rationale. Now, if you're wondering, how am I going to remember all these? How am I going to remember all these? The answer is you'll remember all these by practicing. It takes a lot of practice with synthesis in order to master all of these different nuances. Okay, blocking groups. This is still section 18.11, blocking groups, but blocking groups are going to be really handy when we're looking at synthesis problems. Now, let's say you wanted to do this reaction with this big old question mark over it. You've got a tert-butyl group, so you've got tert-butyl benzene, tert-butyl benzene. And you want to brominate it ortho. Well, we know that if we were to brominate this, if we were to just treat this with bromine and iron tribromide, based on sterics, we're by far going to get the para substitution as the major product. Why? Because this big old T-butyl group is so sterically hindering. Okay, we're going to get this as the major product. Major. How would I go about getting product? There's got to be a way, or you wouldn't be talking about it, Mr. Deon. Oh, there's a way. Okay, and the way that we do that is we install what's called a blocking group, not a protecting group, right? Remember the protecting group, the silyl ether that we looked at way back in the alcohols when we were discussing Grignard chemistry. No, this is a blocking group because it's going to block the para position from being substituted. And in fact, it's even going to promote bromination at the ortho position with respect to that tert-butyl group. So overall, what we would do is we would take our tert-butyl benzene, we would put on a blocking group. Okay, so now we've got a blocking group, and you're like, what's the blocking group? Well, just look ahead a slide, okay? Then you would do the bromination, force the bromine to go ortho to the tert-butyl group, and then you remove the blocking group. What's the blocking group? Well, we talked about it last class. It's the sulfonic acid, okay? So the SO3H group, okay? If you can't remember, again, this is a sulfonic acid, okay? How do we put a sulfonic acid group on? Remember, we use concentrated fuming sulfuric acid, which is a mixture of sulfur trioxide and sulfuric acid together. We put on the sulfonic acid, but what do we know about a sulfonic acid? If you go all the way back to table 18.1, I actually talked about it earlier today and said that it was a deactivator, right? Said it was a moderate deactivator. So we could write that in here. We put moderate deactivator, and it is a meta director. Okay, so I'll give you a second to take a look at the synthesis that's shown below. Now you can see that we're starting out with an ortho para director. We're going to install a meta director. So now we've got a meta director and an ortho para director. What's the para position from the T-butyl is blocked. So that means it's going to direct at the ortho position. And that position also happens to be meta to the sulfonic acid. Everything's set up perfectly. So now we can simply brominate and then remove our sulfonic acid using dilute sulfuric acid. Give me a thumbs up if you think that's a pretty cool synthesis. Eric, we're going to address that, okay? We'll talk about all the possibilities. All right, there we go. Are you asking me what if a strong deactivator is used like nitro? Do you mean as a blocking group? Because the only group that we look at that could be a blocking group in chemistry 3111 is the sulfonic acid, because we don't have, I guess we could use the nitro as a director and then we could reduce it to an amine, but we don't use a nitro as a blocking group. We could use it as a directing group. And if you're like, what's the difference? The nitro group can direct to the meta position, but we don't have an effective way to just remove a nitro from the molecule. Whereas the sulfonic acid, we can install it and we can remove it. Okay, so that's the difference there. And don't worry, I have a whole slide that summarizes directing effects of groups that you can change the functionality, and we'll look at that later. Anyhow, let's take a look. Ooh, it's getting interesting now. Okay, for each compound below, identify which positions is or are most likely to undergo an electrophilic aromatic substitution. You can just see how the people who write the ACS final exam, how easy it would be for them to write a multiple choice question based on this, right? Very, very easy to write a multiple choice question based off of this. Okay, well, let's take a look at the first one here. We've got a methyl group and we've got two nitro groups. The methyl is a weak activator and the nitro groups are strong deactivators. And the methyl group is an ortho para director. This is an ortho para director. Both of the ortho positions are blocked. And so that's going to promote, electrophilic aromatic substitution, para, with respect to the methyl group. We have the two nitro groups. Sorry, somebody in my family is printing something. We have the two meta groups that are strong deactivators and are meta directors, and this is the meta position with respect to those. And so this is going to be the position where electrophilic aromatic substitution will occur, like that. So we'll write here EAS. That's where electrophilic aromatic substitution will occur. Okay, let's take a look at the next one. We've got what? We've got a methyl group. The methyl group is an ortho para director. This ortho position is blocked. This para position is blocked. That would leave us with this position right here. That is the only group on here that's an activator. It's a weak activator, but it's still an activator. Remember, we always go with the stronger activator. and the nitro groups are deactivators. Now, where would the nitro groups, where would they activate towards? And this nitro group here, again, the nitros are both meta directors, okay? This meta position is blocked, this meta position is blocked, but both of them are going to direct meta to this position. And so that is the only position where electrophilic aromatic substitution will occur. I'm going to stop right there. Are there any questions about either of the first two? Okay, it's kind of like a decision tree, right? But these, I would say these first two are examples that are abundantly clear because all of the substituents are directing to the same position. Give me a thumbs up if you follow me. Even a good chunk of the way. Anybody? Maybe I need to scroll down here. Oh, good. All right. Makes sense. Okay, good. All right. Yes, the nitro and the methyl in both of these cases, these first two cases, they're directing to the exact same spot. So let's turn up the heat here and look at a couple other examples. Okay, so we'll start with, let me use, I don't know, yellow. Okay, so we'll start with this ester, and you can see that we have an electron withdrawing group, right? So this is a moderate deactivator, and a moderate deactivator is going to direct to the meta position. Where are the meta positions? This meta position is blocked. This meta position is open. Now, is there anything on here that's activating? And in fact, there's something that's actually a moderate activator, and that's this group right here. And if you're like, well, that's an ester too, hold on. Look, they're very different. This ester has the carbonyl directly attached, which is electron withdrawing, and this ester has this oxygen directly attached. That oxygen is electron donating. And so this ester that I have circled in green, this is a moderate activator. Moderate activator like that, which is going to be ortho para directing. Look, here are the two ortho positions. Here's the para position. So this is the only ortho position that's available. Okay, I'm going to delete my other circles right here, okay, because that's the only position that's available. So what I have circled in yellow and what I have circled in green are both directing to this spot that I have circled in yellow and green, okay, this spot at the bottom. Now there's one more group, and it's a methyl group, okay? Now that methyl group would be directing to the ortho positions or the para position, but what do we know about that? That is a weak activator, okay? And this is a moderate activator, and so that's going to be the king of the castle, okay? And so our electrophilic aromatic substitution is going to occur at that position. All right, let's give one more, the old, college try here. What do we got? Let's do this one a little bit quicker. By now, you're probably partly familiarized. We've got a nitrile. Does anybody remember if a nitrile is activating or deactivating? Would a nitrile be activating or deactivating? Is a nitrile, yeah, a nitrile is electron withdrawing, yeah. So it's deactivating. It's a moderate deactivator, okay? It's a moderate deactivator, and so it's going to direct to what? To the meta positions like this. And look at these. Look at these two methyl groups. I got two methyl groups. They're both weak activators, so they're going to dominate, weak activators. Activator, okay, but where are they directing? They're directing to the ortho positions and to the para positions. So the electrophilic aromatic substitution is going to occur at either one of those carbons. I'll just label one of them because we're assuming monosubstitution, and so our electrophilic aromatic substitution will occur there. All right, kind of fun. You really have to know. You have to know. We'll put here must know table 18.1 in order to fight your way through this kind of problem, okay? To know where substitution is going to occur. Let's see here. Same question. Same type of question. For each of the following compounds, determine the position that is most likely to be the site of an electrophilic aromatic substitution. Let's do this one kind of quickly. We've got, let's just go with the strongest activator of all of them. That's going to be this guy right here. This is a strong activator, which is going to be ortho para directing. Here are the ortho positions. The para position is blocked. We have a methyl group, which is a weak activator, and it's going to be ortho para directing. Here's an ortho position. Here's an ortho position. The para position is blocked. So far, this is going to be our #1 position. And the nitro position, or the nitro group, is deactivating, so we won't even consider that. And so this will be the site of our, come on, what is going on? There we go. This will be the site of our electrophilic aromatic substitution. Let's take a look at the next one. This is going to be our strongest activator, strong activator, which is going to be ortho para directing. Here are the ortho positions. The para position is blocked, so we'll remove that. Then we have a weak activator, or sorry, a weak deactivator. Sorry, my bad. So we'll put weak deactivator, a halogen, which is also ortho para directing. This ortho position is blocked. This one, para position is blocked. This ortho position is open. But again, the methoxy is so much more strong of an activator that, and we're not even going to worry about the nitro because that's a deactivator. So we'll just take this and we'll say this is going to be the site of our electrophilic aromatic substitution. The last two, they both have carbonyls on them. So they both have moderate deactivators. Each of these are moderate deactivators. And moderate deactivators are going to be meta directors. And so I'd say that based off of sterics, right? Because think about it, this group is going to direct to these two positions. This group is going to direct to, oops, I meant to use a different color. Come on. This group is going to direct to these two meta positions, okay? Because both are moderate deactivators, like that. And based on sterics, okay, since this group is so much bigger, okay, bigger group, we're going to get our electrophilic aromatic substitution at this position, just solely based on sterics. All right, there we go. Which one are you referring to, Eric? Which letter? Oh, for A, yeah. For A, it's not going to happen at the one that's highlighted in yellow because we rarely get substitution in between two groups. You have both of these groups here that's going to sterically hinder that. Okay, there we go. Okay, let's see here. Let's try some blocking group chemistry. It says determine whether a blocking group is necessary to accomplish each of the following transformations. We're taking this molecule, isopropyl benzene, which I keep telling you is called cumene. If you want to put a nitro group ortho to that, do you think we're going to need a blocking group here? Yay or nay? Who says yes? Who says no? Does anybody have an inclination? Would we need a blocking group here? Yeah, Mauricio says yes. Okay, a bunch of people are saying yes. I couldn't agree more. We're going to have to take that cumene and I'm kind of running out of space here already, aren't I? Let me just write it up here. So if I start out with this molecule, my isopropyl benzene or my cumene, and I treat that with fuming H2SO4, okay, I'm going to produce a sulfonic acid. Since the isopropyl group is orthopara directing, but it's big, it's going to direct it to the para position. Now I have my sulfonic acid. Again, this is an orthopara director. This is a meta director, so it's going to direct, they're both going to direct to that position. And so now I can do my nitration, which with my sulfuric acid and nitric acid mixture, like that. And I end up with the nitro at the position where I want it. Comme ça, as we say in French, like that. And then I'm just going to remove dilute sulfuric acid, and then I'm going to end up with this product right here. Okay, So let me draw a line here because it's kind of scratching all over the page. What about the one on the bottom, B? Do you think you need a blocking group here? Somebody has their mic unmuted. If you could mute it, please, that would be great. But do you think you need a blocking group here? Yeah. Negative. No, I agree. I couldn't agree more. Don't need one, right? Because this is an ortho para director, and this is the para position. And we're not going to get much ortho product because the isopropyl group is so large. And all we have to do is treat that with bromine, Br2, and FeBr3. Done. Just like that. Boom. Okay? Nothing to it. All right. 9:02. We got 3 hours left. Perfect. Here's a pretty heavy slide. You know, you're probably thinking, maybe you should just stop here, Mr. Deon. This is a big slide. Okay, there's a lot of information on here. This is section 18.12, which deals with synthesis strategies. There's all kinds of different strategies that we have to take in synthesis in this chapter. And we still haven't finished learning all the new reactions because there's 2 sections at the end, no, 3 sections. 18.12, sorry, 18.13, 14, and 15 that we'll have to look at on Monday. But anyhow, are you able to place the blocking group at the ortho position? No, generally speaking, it's going to go in the para position from a director like I had shown before. Okay, so here are all the reactions that we've learned. We've learned bromination, chlorination. Let's get the old check mark here. What did we learn? All kinds of stuff. Good stuff. Learned bromination, chlorination, nitration, the formation of a sulfonic acid or sulfonation. Friedel-Crafts, so this is Friedel-Crafts alkylation. Friedel-Crafts acylation. Okay, we learned the Clemmensen reduction. What else? We learned how to reduce a nitro to an aniline using iron or zinc and HCl, and then working that up with. We learned way back in chapter 17, we learned benzylic bromination, so treating a benzyl derivative with N-bromosuccinimide. So if you treat toluene with excess NBS, you'll convert all of those benzylic hydrogens, all 1, 2, 3 of them. I'm not going to draw them in. You would convert all of those to bromines. What else? We learned benzylic oxidation in chapter 17. So that's chemistry we learned for the last chapter. And you would, of course, if you have at least one benzylic proton, you can do an oxidation like that. Okay, so lots of good chemistry there and lots of options. Okay, lots of different options for reactions here. Okay, well, let's move on and talk about some synthesis strategies. I always find that this section, the synthesis strategies, is a little bit of an FYI, but I think there's some good points here that we should cover as a group. So let's go through this together. We'll probably be able to cover this before the class is over. Synthesis of disubstituted benzene rings requires careful analysis of the directing effects to decide which group to install first. Right? We have these 2 groups that are meta. These 2 groups are meta to each other. Okay, and so we're going to have to install the meta director first. If we put the bromine in first, then we're going to get the nitro going to the ortho or para position. And so we have to be able to look at the substituents and make those kind of decisions quickly. Now, this is a slide that I was alluding to earlier on, which talks about ways that we can change meta directors to ortho para directors and vice versa. If we have a nitro group, so I'm starting right here on the top left. If we have a nitro group, that's a meta director, a deactivator. If we reduce that using zinc or iron, okay, in HCl, and then treating that with sodium hydroxide, we can make aniline or an aniline derivative. An aniline, and then the amino group is an ortho para director. Look at the next one. We have a methyl group on toluene, which is ortho para directing. We could do a benzylic oxidation. Remember, that's a chapter 17 reaction. We can convert that into a carboxyl group, and the carboxyl is electron withdrawing, and so it's a meta director. What else? If we have an acyl group, okay, from Friedel-Crafts acylation, that's going to be a moderate deactivator. and a meta-director. But if we reduce that using a Clemmensen reduction, then we have an alkyl group. And alkyl groups are ortho-para-directing. And what else? Here with a methyl group again on toluene, which again is an ortho-para-director. If we treat that with excess NBS, we do a tri-benzylic bromination, if you will. Again, this is a chapter 17 reaction. We could make this tri-bromo-toluene, and that's going to be so strongly electron withdrawing that it is going to be a meta-director. Okay, so again, I think you should be fully aware of everything that's going on this slide moving forward. Additional consideration is required when one of the groups requires more than one step to install, right? We don't have a method. We have no method for installing an amino group, in one fell swoop, in one step. We don't have that. We can do it in a couple of steps, right? We could do a nitration, and then we could reduce that nitro group using zinc and HCl, and then following up with sodium hydroxide. Okay, so again, we'd have to make some really careful decisions here because these two groups are meta to each other. And if you look at these, this is an ortho-para-director, and this is an ortho-para-director. And so that tells you that, you're going to have some kind of intermediate. Okay, so what would we do? First, we would install the nitro group. But now, if we were to stop the synthesis and hold the phone right there, if we were to treat that with conditions for chlorination, we would chlorinate at the meta position. Then we could reduce it. Okay? And if you're wondering, what do you mean by that exactly? Well, that's what's shown right here. So first, in the first step, you would treat that with nitric acid and sulfuric acid. And in step 1, you would end up making the nitro product. I'm just kind of walking you through it here a little bit. Then you would chlorinate that. So step 2, and you would chlorinate at the meta position like that. Okay. And then step 3 and 4, you do the reduction followed by the basic workup, okay, to remove the proton from the aniline. In most cases, changing the order of the reactions will change the substitution pattern on the ring. This is one example where you can see you really have to know all of these reactions kind of frontwards and backwards in order to do the synthesis effectively. What other limitations are there? Okay, there's some more exceptions to the rules. So other limitations. So I want to draw your attention to this because these are important. Other limitations that must be considered when planning a synthesis. First of all, nitration cannot be done on a ring that already contains an amino group. And the reason why you can't do that is because that amino group can be oxidized in the presence of nitric acid and sulfuric acid. If you're wondering, should I know this? Oh yeah, you should know this. So we're going to know this limitation. So you can't nitrate an amino, even though it looks like it's a beautiful ortho-para-director. Some other limitations with Friedel-Crafts. It says Friedel-Crafts do not work on a ring that is strongly deactivated or moderately deactivated. So anytime you have a deactivator, unless it's a weak deactivator, you're not going to get a Friedel-Crafts reaction to work. They just don't work. Okay, I can tell you that from personal experience. Here we have a moderate and a strong deactivator. We're trying to add a methyl group using Friedel-Crafts chemistry. No, it won't work. Okay. So with that in mind, we can take a look at question 18.26. 18.26. How do we make this compound? Okay, we'll do the first one. Kind of interesting. We get an amino group, which is ortho-para-directing. Right, this is an ortho-para-director. And then we have the bromine, which is an ortho-para-director. But we know that the only way that we can get that nitro group or get that amino group is from a nitration and then a reduction. Now, if we had the bromine, if we just had bromobenzene by itself, and we can make bromobenzene pretty easily, okay, all we do is take benzene and we treat it with bromine and iron 3 bromide, like that. We would end up with this compound, like that. Okay. If we just tried to nitrate that, if we just treated this with nitric acid and sulfuric acid, like that, would we get the nitro exclusively in this position? The answer is no. We're going to get some para product too. And so is there an end run that we can do around that? And the answer is yes. If we sulfonate that, right? If we treat that with fuming H2SO4, we can put a sulfonic acid in the para position. So then we would have this compound like that. And then we have a meta director to these positions, and we have an ortho para director to these positions as well. So now we're set up to treat this with nitric acid and sulfuric acid like that to give you this compound where we have the bromine, we have nitro, and we have the sulfonic acid. Now it's just a matter of removing the sulfonic acid with dilute sulfuric acid so that we end up with the ortho substituted nitro group and bromine. And then in the last step, you're going to treat that with iron or zinc and HCl in the first step. And then you have to treat that with aqueous sodium hydroxide like that.